应该有，应该有。
你看，这五个对方没看到。
有，现在开始。
可以的。Okay, let me just continue to explain the questions from the student. If you recall this slides, this slides is just like your homework. So you do have like M is 2 by 2, and Zeta is 2 by 2, K is 2 by 2, and BF is 2 by 2 like that. Now this is all coupled together, coupled through this damping matrix and stiffness matrix. However, now this system has a little bit different because when you have introduced this transformation matrix, that means my mass matrix, K matrix, I can diagonalize it, I can diagonalize it, I can diagonalize it. Then through this second order, I didn't convert it to first order. This one, I didn't convert it to first order. But for your homework, you cannot, for your homework, you cannot simultaneously diagonalize all three metrics. That's not your homework. But the reason I show you this is the following. Assume that you can simultaneously diagonalize all matrices. Then this couple matrix become, through this psi matrix, will become two decoupled second order equations. Now, from these two decoupled second order equation, then it's clear that my natural frequencies for the first one is 1. My natural frequency for second equation of this one here is the square root 3, right? Agree? So that means if you look at this, look at this system without coupling, what is the natural frequencies of this one? If I assume I don't have any coupling, then that means 1 divided by square root of 1 is also 1, something like that. But for second one is 1, this is square root of 2, but this is square root of 3. Now for any coupled system like this is coupled system. They can always decouple, become by eigenvector matrix. You can decouple your matrix like AC. You can decouple your matrix, become the like this kind of first order equation like this. But this is second order, and this is assume you can simultaneously diagonalize all the coupled matrix. Then you have such luxury to see their second order equation like this. But there's a technique from here too. There's one way, some way to do it. They can do it from this kind of first order, and I can write in terms of second order. In other words, I can base on lambda 1 and lambda 1 star, this one, each pair. I can convert it through this guy. I think I also give you this information. How can I compute the natural frequency and damped? I think did I? Yeah, here. Here is the definition of natural frequencies and damped frequencies and damping ratio. So if I have a damped frequencies, I told you that I have a damped frequencies. So where is my damped frequencies here? Okay, now look at this one here. Lambda 1, lambda 2 is my eigenvalue. If I have eigenvalue, lambda 1 and lambda 2 is my second eigenvalue, which is complex conjugate, for example, then, but this is not. Let us look at a complex conjugate. This is overdamped, this is critical damped. Then let's look at the, where is my endodamped? Is that endodamped? Endodamped. Where's my endodamped? No. Okay. Where's my endodamped? Okay. This endodamped here. Okay. Now, this is my endodamped frequencies. I have lambda 1 and lambda 1 star, and this is my damped frequencies. So if I have my damped frequencies, I have lambda 1 and lambda 2, I will be able to compute the omega n and zeta n, because I have this WD is my W, my imaginary part of lambda 1. And then I will be able to solve this. If you use this equation, I will be able to come back to solve natural frequencies and also damping ratio. Agree? So that is just give you the idea of the eigenvalue and natural frequencies and the damping ratio. So for each eigenvalue you solve from here, a pair of eigenvalue, that means lambda 1 and lambda 1 conjugate. Then you can use this formula to solve your natural frequencies and to solve your damping ratio. Understand now? Any problem? Agree? That's there. All right. My omega d here. Okay, right down here. From this chart. Okay. My lambda real part equal to minus theta n omega n. My lambda imaginary part is equal to omega d. Right? If you look at that formulations, this is the formulations. This is the damping ratio. If I say this is 0.05, I know this, I know that. I will be able to solve this. I will be able to solve that. Omega d is 9. Then omega n and omega d relationship is depend on delta n. So what is this one? We have WD equal to Wn square root 1 minus the square, right? So I have 3 equations, 1, 2, 3. I know this one, I know that one. If I give you this one, if I give you this one, this is right. I know this one, I know that one. Then I know the omega d, that's omega d. If I give you this, I can solve omega n. Agree? So you have 2 pair in your homework. You have 2 pair eigenvalues. That means you have 2 pair omega n and omega d, and your lambda r and lambda I. You have the imaginary part and the real part. Any problem now? You can switch back. Okay, so let us look at this. So let us look at this guy here. If you look at this is my solutions, final solutions. If you want to write this way, that final solution is nothing but the real power eigenvalues, all right, times the imaginary power eigenvalue, A1 cosine omega dt plus A2 sine omega dt, and omega d is my eigenvalue, the pure imaginary power eigenvalue. Does that answer your question now? So this show you eigenvalues, the relationship between eigenvalue, damping ratio, natural frequencies, and so on. So each pair of eigenvalue, you can look at them as a second order, the equation of motions. You can represent it like that. Maybe I need to write something more clearly to explain in physical sense. That's better. This is not a physical sense. So let us stop here. Then I need to continue our lecture today. This is just homework, but it's good for you to think about it. That's good. And the question asked, this is good questions. That's really important to understand the physical meaning. Okay, let's go back to our lecture today. Let's go to the state space model, because the homework 6, they go to homework first.
So homework 6 first?
Yeah, homework 6 first. Let's go to homework 6 first. Let me explain this homework 6. Okay, let's explain this homework 6 first. All right. This is the same as your homework 5, and I want you to convert it to the continuous time state space model. This is second order. Continuous time state space model is first order. Then I want you to have a discrete time state space model with delta t equal to 2 seconds. Then I ask you to do simulations for 1,000 sample point with the input accelerations is for this one. And of course, I use the second order time step, use a discrete time state space model to do simulations. And the discrete time state space model is very easy to do simulations. It's algebraic. You don't have to integrate your equations. But to convert this from a continuous model to discrete model, that's something you have to do it. It's easy to do. For formulation is in the notes already. You can convert it quickly because that's AC is invertible when you convert it. Now, the homework problem 2, and this is easy too. I will show you how to do this very soon. I mean, observer model. And this observer model is important because that observer model is the one to be used for feedback purpose. When you have state which is not measured, you have some state you don't measure it, then how can you estimate those states? And that's we call the observer model. So this observer model will allow you to do the state estimations. Now, remember this. I already give you this discrete time model, A, B, C, D. That's a discrete model. Now, I want you to perform write an SCI lab program to compute the time history. Just only 1, 2, 3, 4, 5 inputs. Simple. I have only 5 inputs. just these 5 inputs. But my initial state is 5 and minus 1. That's my initial state. So you have initial state, you have input, then you will be able to do simulation for this. So I'll show you very soon now. And then I want you to solve this 2 by 2 matrix to get Z1 and Z2. And as soon as you got a Z1 and Z2, you can do what we call the state estimations. And this is state estimation equations. But the only difference is between this one and that one is my initial state is different. This initial state is 5 minus 1. This initial state is 0, 0. So initial state, you don't estimate initial state. You start from initial state, then you estimate after initial state. And then you will be able to see how accurate your estimate state will be after initial state. And I will show you the example in the lecture soon, so you will be able to see it now. Okay, let us look at the our lecture today. This is also a very simple problem, easy to write a problem. Without the state space model.
Okay.
Yeah, that one. No, that's not.
This one?
This one. All right. Now we need to skip. Yeah.
Oh.
Let us look at the. I will start with. That's yeah. Okay. Now let us start from here.
Okay.
Okay. The let us start from here. This because this is related to your homework. Now you have continuum model, which is first order equations. But you have a continuum model, the second order, then convert it to first order. That's the one way to do it. So you can convert it like this. Discrete model, I will show you, I will prove to you the discrete model. I'm not going to repeat this. Okay, the discrete model. Now you can from continuum model, you can solve your discrete model by this. A equal to E ACT. You know AC. I give delta T. So A, just like that. In the Scilab, it's easy too. You can type help XEXP. The type help EXP. They will show you how to do this. The exponential functions. Now, if my memory is correct, you need to do this. A equal to EXP XP and AC times delta T. That's it. That's your A. That's your discrete model. There's an M means exponential, tech M means take the matrix. I think you need to be careful on that. All right. All right. Let's switch back. And then your discrete model B, because AC is invertible, you can just simply do this step. AC inverse, then parenthesis A minus I. This is identity matrix times space C. That's all. That's your B. Easy to convert it. So in your homework, these two equations give you the formulation to convert it. Although that there's in Scilab or MATLAB there's a command. They will convert it for you. Convert it from AC, BC to A and B. There's the function to do that. You can search for it, and they have so when you compute A and B, you can also use the Scilab existing function to check, see if A and B are correct. All right. So I already showed you about this, and that's already done. And last time also I showed you the discrete model for the vibrational motions. All right. Now this is simulations. That's it. Those are simulations. Although I start with x0, but your program, Scilab, you don't start with 0, you start with 1. 1 is the initial state. So this is, if you look at this one carefully, when k equals to 0, then a x0 plus b0, that becomes a x1. And go to x2 means a times x1 plus bu1 becomes x2. x3 becomes a x2 plus bu2 becomes x3, and so on. That's all. That's your simulations. You can just write a loop to compute your states, right? This is a simple program. You need to write it. And of course, that if you sub x1 from here to inside this equation, then it become all like that. Just what I want to do here is, on the right-hand side equation, I don't want to have any state in that equations. Then this is I sub the state information into here. Then there's no state here. And the same thing for x3. If I submit this one, except initial state, there's no state here. So you keep sub into those combination. Finally, you got this one. Xk equal to a xk minus 1 plus b uk minus 1. Then you have ak k times x0 plus ak minus 1 bu0 and so on. You have now no state involved here. You have input, all input, all input, all input, but no state. But this is initial state. All right, and so on. All right, look at this. This is what we call transient response. Now, transient response equivalent to your homogeneous solutions. This is like we call the forced response. Forced response that's corresponding to your particular solution in your differential equations. If you x0 is 0, if you don't have any initial state, means you don't have a transient response, means you don't have any homogeneous solutions in this system. And normally, that we really don't worry about transient response because in any physical system, they do have some damping. So your transient response supposed to be gone sometime later. So we will focus on the forced response. So all the control are based on the forced response to design your controller. We are not based on the transient response. This is just terminologies. This we call transient response. This is what we call forced response. Again, transient response comes from your homogeneous solution of your differential equations. Forced response comes from your particular solutions. Okay, now let us look at observer model. So this is the way this is the way you learn how to do state estimations. Now, that's my the state space equation. Axk plus buk. Then I have gyk minus eyk. I add 1 gyk and I subtract 1 gyk. That means I do not change my state equations. Do I? I don't. I did not change my state equation at all. However, now why I want to do this, I explain to you. This G is my observer gain. Later on, this G will be my observer gain, GAIN. That's my gain matrix. All right. Now, when I sub 1y, I sub 1y equal to cx plus du. If I set 1y equal to cx plus du, just one y. This y, I sub this y into that equations, then I have this. See, this is arbitrary at this moment. Then I can define. Then I can define the a plus gc xk and then plus bgd uk. Let me just explain a little bit here so you will understand better. So I have x, yes, x k plus 1 then equal to axk plus buk. Then I have g yk minus g yk. All right. Then I will say axk plus buk plus g. Then yk is equal to cxk plus duk minus gyk. All right. Then that equal to a plus gc xk then plus b plus gd uk minus gyk. All right. So this one here, I sub that one into there. Then that provide me a plus gc xk plus b gd uk. All right. Now, this one here, later on, this one measurement. Can they see it here? I hope so. I think they can see it. All right. This later on, this will be from measurement, and this one from estimate. That's why I write this way. Because from estimate that y k equal to cdk cxk plus duk. All right. Now, okay. Now understand about this. Any question about this at this moment? Any problem now? Now here we assume that estimate identical to the measurement. That's not true later on. But in theory, you say, okay, I'm going to derive my equation of motion such that I have gyk, but one yk is from estimate and yk from measurement. Assume they are identical, and in theory, then we can do that. That's in theory. Okay, now they'll switch to our okay. Now, so if that's the case, that's just like in my whiteboard, and that's the formulation we got. And if I put the a bar equal to a plus gc, then my observer equation become xk minus xk plus 1 equal to a bar a bar xk plus b bar vk. But that v well, wait a second. That V is UK and YK. We stack them together. So this VK, well, including my UK and including my YK. And B bar, if you look at this B bar is B plus GD minus G here. And well, UK and YK are all for measurement. U for measurement, Y for measurement. So if you look at this one, XK plus 1, A bar XK plus B bar VK. Now, let me write down again here. Let me change this. Okay, let me just do this. Now, I can write this one equal to A bar XK, and this A bar is this. Then I can write this one in terms of B plus GD, and then minus G here, and then I have the UK, I have YK here. All right, and this UK and YK, both of them from measurement. All right, this is both of them for measurement. So I can write this equation become like this. So X bar, that's A plus GC, B plus GD minus G, UK, YK. And again, this is from our measurement. That's available from our measurement. And this XK and so on. All right, understand now? That's any questions so far? Any questions so far? No? Okay. This is in theory. All we are talking about here is in theory. In theory, that we assume that estimate and measurement are identical, and then you can write this. That's my theory. In practice, it's not like that, but anyway, this is the way we derive the observer. Okay, now let's switch back. All right. So from the whiteboard here, then you will be able to see that that I can write observer equation become this: xk plus 1 equal to A bar xk plus B bar, and B bar defined to be B plus GD minus G, and my V, it will be U and K, and I stack them together. All right. Now, of course, we can if we do the coordinate transformation like this, it doesn't change it doesn't change V, U, and Y. You can change Z, you can change state. Any coordinate transformation, you can change from X to Z, but you will never change your V, your U, your Y. So those are still there. Okay, let us look at the next steps. So observer equations. The same thing, if you look at these observer equations, I can do the simulation like this. This is exact the same simulation as you get from, as like I show you just last slides for your state estimation. Exact the same thing, except now we have A bar. I didn't tell you what is the G yet. I will tell you later, very soon, what kind of G we can use for that. But this is the same thing, exact the same thing as your state equation without observer. Now, again, we do have a transient response. We do have a forced response. But now, this transient response and forced response, we have bar, and we have B bar, and we have V. And V here is for measurement. Y here y here, this is my estimated. So all the left hand side, x and y, that's my estimated. All my right hand side, all from measurement. Okay, that's a discrete model. Let us look at the some example. Observer model. Okay. Then here I provide you a G. I provide you a G. And how can I compute this G? I'll show you soon. What kind of G I can use? What kind of observer gain G I can use for my observer model? That's important. The observer gain G will be the one determine how fast or how accurate you can estimate your state. So in terms of speed, in terms of accuracy. So if you choose a good G, then your estimation will be very fast. Your estimate state will be very accurate. Then what kind of G is a good G? Good observer gain. So the whole control methods, you just about observer gain, you can find a book, maybe that thick, more than 300 pages. Just talk about how can you design observer gain for your state estimations. But here I'm gonna just show you one method. All right. Now, if you use this observer gain G here, that's, I say G here. I assume that K equal to 1, M equal to 1, delta T is variable. The delta T is variable, any values. All right. And then my A, you know that, I will show you the discrete model for a spring system with M equal to 1, K equal to 1. Now, your discrete model will be cosine delta T, sine delta T, minus sine delta T, cosine delta T. Your B will be 1 minus cosine delta T and sine delta T. C will be minus 1, 0. Assume we have acceleration measurement and D equal to 1. So by some reason or by some magic, you agree that this is the G I want. And then we'll see what happens. Now, if I give you the G called 2 cosine delta T and minus sine delta T for second terms, plus cosine square delta T divided by sine delta T, that's my G. G is 2 by 1 vector here. So A plus GC means A is this one, and G is this one times C. G times C will be this G times C, a column vector times a row vector. A row vector becomes a matrix. And that's my A bar. And this is my B bar. B plus GD, just follow these formulations, you get a plus GD. Okay, let us look at the what is our results. Here, I show you A bar square. A bar square will be equal to 0, 0, 0, 0. That's kind of magic. See that? A bar equal to 0, 0, 0, 0. Now, if you don't believe me, you can go to multiply it and see it is true or not. All right. Let me wait a second. Just let me see. Wait a second. Don't switch. All right. Let us look at this. This G is very interesting G. All right. This G is wait a second. Don't change. Let me copy this. A bar equal to G DC. Let me copy this one before you switch. So I can see it. A plus GC. That's from there is minus cosine theta t and sine theta t, and then this is minus cosine square theta t, and then sine theta t, and then cosine theta t. Okay. Okay. Now you can switch that. You can switch that. Now a bar square equal to minus cosine theta t sine theta t minus cosine square theta t divided by sine theta t, and then cosine theta t, and then I multiply itself cosine theta t sine theta t, and then is cosine square theta t sine theta t cosine theta t. Now I grant this equal to 0, 0, 0, 0. Or you can simply just multiply together and see what happens. They are 0, 0, 0, 0. Okay, and this is this exact why I choose this G. Okay, you multiply this one by this one is 0. Multiply this one by that one is 0. Multiply this one by that one is 0. Multiply this one by that one is 0. Right? Agree? Oh, agree, right? So that's G. If I don't give you this G, you can also solve by yourself. I say, well, I don't know what kind of G I want, but a bar square becomes 0, 0, 0, 0. You can go back home and solve it. You will get my G exactly the same as mine. I give you A, I give you C, I don't give you Z, but I say a bar square must be 0, 0, 0. And when you go home and solve it, you will get the exact same as my G showing on the slide. That's exactly the homework I asked you to do. The 6B. I give you A, I give you C, then I say I want a G such that 0, 0, 0, 0. As a matter of fact, that's exactly the same solution as this one anyway, so doesn't matter. All right. Okay, now let's switch back to the lecture notes. Okay. Now, when we agree this, then let's look at the observed for state as dimensions. That's my equation of motions. And look at state as dimensions. All right. Just focus on the hat. I write x hat. All the quantity with hat means that is the estimated state. See, this is the true equation of motion. This is the estimated state. It's not the exact same as that one. So I write as state as dimension with hat. X hat k plus 1 equal to a x hat. Assume I give you a hat plus b uk plus g y hat k minus yk. Without hat means that's from your measurement. Okay? Without hat, that means from your measurement. With hat, the y hat is computed by cx hat plus duk. U is also from measurement. A, B, C, D is giving. G is you compute it, you choose it, you whatever you get it. All right. Now I'll stop here, let you think about it for 10 minutes.